Okay, in this video I'm going to show you how you can implement the no pooling, full pooling, and beta binomial models for customer purchasing while customers are alive. Again, the high level framework here is we have customers, and for each customer we observe the number of purchases they made out of a certain number of purchase opportunities. We're going to assume that we have the number of future purchase opportunities over some future horizon, which is probably going to be coming from some sort of a retention model. And the goal is to predict the total number of purchases over that holdout period. So the question is, how do we predict this? So again, under the no pooling method, we're going to estimate the purchase rate for every customer by their historical purchase rate. So just x divided by n. So here we're not doing any pooling. Every customer's purchase rate is determined independently of every other customer. Then the number of purchases that we expect in the holdout period is just our expectation for p multiplied by the number of purchase opportunities in the holdout period. So that's what we did over here. We're just going to use that same formula for all the other customers. Then the squared error is exactly what it sounds like. It's just my expectation for purchases in the holdout period minus what I actually saw in the holdout period squared. So there we go. So here we predicted 7 purchases. We actually saw 5. That's a difference of 2. 2 squared is 4. Now under the full pooling method, what we're going to do is we're going to get the global average purchase rate. We're going to get that by summing up the total number of purchases, dividing it by the total number of purchase opportunities, like that. So again, x total is the sum of the x's, n total is the sum of the n's. Then my global average purchase rate is just x total divided by n total. But I'm going to hammer those down. I'm going to anchor those down so that they're the same for every customer. So every single customer has the global average purchase rate. Then E of x star is just my expectation of p, again multiplied by n star. Exactly the same as the no pooling method. And the squared error is again expected minus actual squared. So hopefully that makes sense. Now the two things that I'm just giving to you for free are the probability of observing a particular value of x given n under the beta binomial model and how that translates into E of p. Now E of p, in theory, you've got this from the spreadsheet deck that we presented in class. It's that weighted average of the global average and the local average. But this is just a nice, simple simplification of that formula. So I would go back and make sure that you're able to reconcile the one against the other. So I get my probability of each customer's individual data. I take the natural log of it. That's the log likelihood of each individual customer's data. And then the log likelihood of the data as a whole is just the sum of the individual log likelihoods for each customer. So right now, I'm going to estimate the parameters of the beta binomial model. So you start with some values, just say 1. And what I'm going to do is go to solver, and I want to maximize the log likelihood of the data by changing alpha and beta. Because I'm making unconstrained variables non-negative, that'll enforce that alpha and beta are both positive. Solve. Oh, it's running into an issue because actually we want to make sure that these two values are strictly positive. So I'm going to go solve, and let's add in a couple constraints. So these both need to be greater than 0.001. Now it should run without issue. There we go. So I'm going to keep that solution. That gives me my E of P. I get E of P for free from the model estimates and N and X. And now, just like the other models, I can just get the expected number of purchases in the holdout period by taking my best guess for a particular customer's P, multiplying it by N star, and then getting the squared error accordingly. E of X star minus actual X star squared. Okay, so how well do we do with each of these methods? So again, the mean squared error is literally just that. It's the mean of the squared errors. We get the mean of the squared error for this model too. The mean of the squared error. And let me just go, this right here is saying BB model. Whoops. Let's make that black. And the squared error for the BB model is just the average of this column over here. And we see that we are doing better. So that's it.